Hey everybody, this is Matt with mattsmath.com. Thanks for joining us here today as we talk about angles of polygons and similar triangles. Dealing with shapes today, we're going to be looking at angles and how shapes can be similar together. We're in the Math Common Core Standard of Geometry, and we're going to be talking about congruence, similarity using specific shapes today. We're going to be looking at real-world problems and how can we use similar triangles to find indirect measurements. Pretty sweet stuff. Our guiding question is going to be talking about using a formula to calculate the angles of a polygon and to see what's unique specifically about triangles and how their angles are similar to other triangles. Alright, here's a sweet little dude. He's looking up at this tree. He's thinking, man, I'd love to climb it. Actually, he's probably thinking, why is this triangle tree right in front of me? Well, what we're going to do today is we're going to talk about how can you measure the height of a tree without actually not using measurements. Not actually getting up there with some sort of tape measure or something like that and measuring the height of the tree. We're going to use what's called indirect measurement to measure the height of a tree with its shadow and angles. It's pretty cool. Alright, first we're going to talk about the sum of a polygon. We've talked about triangles before, and we know that when you add up all the angles in a triangle, you get 180. But how can we find other polygon angles and what the sum of it would be? Well, let's break down a specific shape, like a pentagon, into different triangles and see what happens. Okay? Now remember, a polygon specifically is a closed plane that has 3 or more line segments as sides, and they intersect only at one endpoint. So there's no crossovers or anything like that. So when we look at these shapes, these are polygons. Typically in math we deal with the convex polygons, not these concave ones. Notice concave has some sort of indent, like this sweet lightning bolt or this star here. Convex all stick out. They kind of jet out. Does that make sense, the difference between concave and convex? Whereas these are not polygons over here. They have intersecting lines, they're curving, like this one is intersecting lines, this one is curving. They must all be line segments, okay? So that's the difference between polygons and non-polygons. Alright, well here's a pentagon. Why don't you break this pentagon down into triangles? The least amount of triangles that you can. You draw it and get some lines on there. Well, here's one, right? And there's 2 lines making 3. Now what I asked was the least amount of triangles, okay? Now you could make a whole lot more triangles in there by drawing an angle down there and an angle over there and so forth, but you need to consider drawing the least amount of triangles for this activity, okay? Now, with this, why don't you consider how many degrees would be in it? Can you figure it out just by looking at the triangles there? Alright, well how many degrees are in that top triangle? And the bottom one? And the bottom one? Well, total, have you figured out how many degrees there are in this pentagon? Alright, there are 3 triangles, so 3 times 180 is 540. So in this pentagon, there's 540 degrees in it. Is that true for all pentagons? What about this one? Can you break it down into the least amount of triangles? Yeah, it would be. This one would also be 540 because it would be 3 triangles. What about hexagons? How many triangles can you create in this hexagon? Remember, you're looking at the least amount of triangles, okay? Well, here you'll get 4 triangles. 4 times 180, 720. So in a hexagon, there's 180 degrees, or excuse me, 720 degrees. What about the famous septagons? Sounds like some sort of bad robot or something. The evil septagons. Alright, so how many triangles, the least amount of triangles can you get in this septagon? Alright, there are 5 triangles, so 5 times 180 would be 900. Noticing a pattern about how many triangles there'd be? Well, what about an octagon? Out in the octagon, how many triangles can you put in here? There are 6 triangles, so 6 times 180 is 1080. Seeing a pattern? Alright, well what's the pattern? Well, with a pentagon we had 3, with a hexagon we had 4, septagon 5, octagon 6. So it looks like we multiply 180 degrees by the number of sides, but not the actual number of sides. You're subtracting the number of sides by 2. Okay? So here's your equation. This is what you're going to do. The sum of the angles of an entagon. Now, by an entagon, I don't mean something like I'm stuttering, but an n here would be the number of sides. So 3 would be a triangle, 4 quadrilateral, 5 pentagon, septagon, hexagon, octagon, and so forth. So an entagon is n would be the number of sides that you have, okay? So what you do is you take the n, the number of sides, you subtract it by 2, and then multiply it by 180 degrees. That's for any polygon. So let's look at these. Why don't you try to figure out how many triangles, remember the least amount of triangles, okay? Least amount of triangles here would either be 1 there or 1 there, so it'd be 2. What about here? It's the pentagon. 1, 2, 3. This one's tricky. Remember the least amount of triangles. Well, why don't we count the sides? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12. So it's got 12 sides. You got it? All right. So 360, 540, and that 12-sided figure, 12 minus 2 is 10. 10 times 180, 1,800. Right. Well, looking at that, knowing that you have a pentagon here, and a pentagon is 3 times 180 degrees, find the missing length x. Just like in triangles, when you had 3 angles and you missing one of them, you had 180 total, and you subtract it to get x, do the same thing here with this pentagon. And then do the same thing with this one. Notice you have 2 of the same angles here. You've got 90, 90, 125, 125, x and x. What would x equal? Did you figure it out? Remember, first you got to count the number of sides. You got 1, 2, 3, 4, 5, 6. So it's a hexagon, so 6 minus 2 times 180 degrees would give you the total number of angles, or degrees that would be in here, that your angles would add up to. All right, here are your answers. So on 4, it's 70, and on 5, it's 140. All right. Now let's talk about something just a little different about how shapes can be similar. When we look at pictures, we can see whether something is similar or not just by noticing whether it's distorted or not. You can look at the pictures down below and you can totally tell. So when we talk about triangles now, we're going to talk about similar triangles. Let's talk first about similar pictures. Now if I take this picture here of my 4 kids and my daughter trying to tickle the turtle, isn't he cute? Alright, so you have corresponding similar figures here. A corresponds to A prime over here, B corresponds to B prime, and angle C prime corresponds to C. So notice the shape is similar. It's smaller, it looks the same, right? Just smaller. And you always have to make sure that the same sides match up to the same sides, okay? And these are called similar figures. And they have the same shape, but not necessarily the same size, okay? That's what similar figures are. The angles are equal, and the lengths of the sides are proportional. If we were going to set them up, we could form a proportion with the sides. Now with the corresponding angles and sides, they match each figure. So we'll talk about this saying it this way. A is similar to A prime, B is similar to B prime, angle C is similar to angle C prime, or actually equal. Angles are actually equal in similar figures. And you can notice when things are not similar. You think about drawing programs or graphic arts programs that you might use on a computer or wherever. When you take a picture and you see these little squares, you can actually distort the picture by stretching it up and down or making it wide by this way and making my kids look like they'd be able to play in the basketball leagues. Or here, you've got the kids really wide as opposed to being pretty tall, like they are over here, okay? So you can actually tell just by looking at it that they're distorted, right? They're not similar. Well, with similar triangles, they are corresponding. They have corresponding angles and corresponding sides, and we can study them pretty closely. And there's actually a branch of mathematics called trigonometry that is studied that studies just triangles. It's pretty cool, and their angles. All right, now let's look at these triangles here. If we have these specific sides, we can find the missing lengths because we know that they're similar. Remember, their sides are proportional. So let's set up a proportion. 5 is compared to 25, 4 is compared to 20, so 3 is also compared to this length down here. So if we set up a proportion, 5 over 25, 4 over 20, we can also do this. 3 to 4, as is 20 to x. All right, so what we could do is cross multiply and divide. We find out that what? The x equals, you got it? It equals 15, okay? All right. Why don't you look at these guys? Are these triangles similar? Notice if they have all the same angles, they will be similar. But if their angles are different, they will not be similar. So figure out, are these angles the same? Are x and y? Is 30 degrees y and x 40 degrees? Or this one, you'll figure out whether they're similar or not just by actually looking at it and saying, okay, let's see, 70 pairs up with 50. 50 pairs up with x. 60 pairs up with y. Are those the same? All right. In one, they are, because they all have the same angles. They all actually equal each other. Whereas in two, they don't. They have different angles. Okay. Are these similar? Yeah, they are. And that x is 100 degrees. All right. These triangles are similar. How tall is the tree? This is where you can take an indirect measurement, where you can take the shadow of something, and you can actually measure how tall the tree is. So think about the outer triangle, where the outer triangle has a length of 15 and a height of x, and this lower triangle has a height of 4 and a length of 6. Okay, so now what you can do is you can actually calculate what x is by setting up a proportion. Write a little bit of it down here for you. 4 is compared to x, and then you put the proportion. Then what's 4? Well, 4 goes with x over there. 4 goes with 6, and then the length of this bigger triangle is 15. So why don't you cross multiply and divide and tell me how tall this tree is? Just by knowing that the shadow of the tree is that long, and then that this guy, his shadow, is that long. Well, I definitely encourage you to go out and do this and measure a tree. On a sunny day, measure your length, your shadow length, and measure the tree's shadow length, and you'll be able to tell how tall that tree is. Pretty cool, huh? All right. Cross multiply and divide. And you get that the height of the tree is 10 feet. All right. Well, are you able to find formulas to calculate the angles of polygons and see what's unique about similar triangles? I bet you are. Pretty cool stuff that we learned today, huh? About indirect measurement, especially with the trees. Try it out. Well, that's it as we talked about angles of polygons and similar triangles. This was Matt with mathsmath.com. Thanks for joining us. Check us out on Facebook at Solving Maths Problems. And enjoy math.